Welcome, future secondary educators. This is SUNY Genesio's INTD301, and this is the first of several lessons that put our number system on a fairly firm foundation. Because we can't do arithmetic if we don't know that in fact there are whole numbers, and we don't get to say there are whole numbers because there are whole numbers and that's it, and if you don't like it, you can go pound sand. Instead, we put the whole numbers on a rigorous footing, and we do that in the following way. We define the number that we're going to call 0 to be the empty set. This feels about right, that the empty set and 0 should be correlated somehow. I mean, the empty set, that's just a set with nothing in it. What's in it is nothing, 0. Nothing is in that. So if you were to demonstrate for a small child what 0 was, you would point to nothing and say, there it is. And then we consider the following. We call the successor function S. The successor function, such that S of a set A. So this is a function that operates on sets. The input is a set, the output is a set. S of the set A is A union the set containing A. This right here is the magic. This right here is where the magic happens. This is how you get from 0 to 1 and 1 to 2 and 2 to 3 and so on. Why? Because when we're putting together a number system, we want to do it with as few assumptions as possible. So we assume that 0 is a thing, and we already have a language by which 0 can be a thing. And then we generate other numbers by this successor function. So in the following way, when we think about the number 1, well, the number 1 is going to be the successor function of 0, which is the empty set union the set containing the empty set, which, as you and I both know, is the set containing the empty set. How many objects are in that set? 1. And the number 2 is S of 0. That's the number 1, the set representing the number 1, union the set containing the number 1. And that's a set with 2 things in it. 1 object in this set, 2 objects in this set, and so on. And so inductively, we get every whole number just from defining 0 and creating what is essentially an inductive step. We can generate every whole number in this way. If we want to know what whole number 2021 means, that's easy. We have some representation for 2019, and we run the successor function on that, and it gives us 2000, oh, sorry, yes, if we want to know what 2021 is, we have some representation for 2020. See, I almost skipped over 2020. Most of us would probably rather. And then we run the successor function on 2020. So, by definition, the whole numbers are a non-empty set W together with a successor function from the wholes to the wholes and an equivalence relation. We'll call that equals satisfying these axioms. There are four. The whole numbers contains an element 0. There is a whole number 0. That's where it all starts. S of n is in the whole numbers for every n in the whole numbers, and S of n is not allowed to be 0. 0 is not the output of the S function at any point. If S of m equals S of n, then m equals n for all m and n in the whole numbers. Two different outputs let's try that again. Two different inputs implies two different outputs. The same output implies the same input. And then 4. If k is a subset of the wholes such that 0 is in k and n being in k implies S of n is in k, then the set k is really the whole numbers. So uh, 0 being in k is necessary because it establishes that we start at 0. And then we have this inductive thing where if every time a number is in the set k, its successor is in k, well, if we start at 0, that means that the set k has to be the set of whole numbers. So we build the whole numbers in an inductive way. We put 0 in, and then we have a successor function that builds from 0 and generates every whole number we could possibly imagine. And that puts things on a little bit more firm of a footing. Hope that's helpful. Next up, integers.